Yes, thanks. Okay. So, one thing I want to do today is two things. So, Kaushik, you wanted a review of the random effects model, right? If you
That's
understand
correct.
correctly.
That's correct.
And and okay, we can do that first if you want. Or okay, let's do that first. The other option was to do the two by hand. We'll do that after I finish this. Do the hard thing after I finish this. Let's do that. Let me join on Zoom in my other meeting as well. One second. Give me a second. Let me just do that. Yeah. What's going on? Why is it not joining Zoom? Okay, what's the password? It's 1 1. Okay. See the screen. It's coming. Very good. Let's go. Can you all see the screen? The alert me on chat if you can see or not see.
Yes.
Yeah. Okay. Good. So we can just I'll just give an independent review of the random effects model. Nothing to do with I'll just sort of give an independent flavor from the video that's posted on the website on the course website. So So one of the first features one tries to understand is that why do we need a random effects model? That's something that one has to sort of come to terms with. So I'll do it by an example. Then after that, it might be clearer. We can go back and discuss this random effects model in a certain. You know. So one thing to keep in mind is that in all the models before we came to this, we assumed some sort of independence and sometimes even identical distribution of each point data set. So we didn't understand, there was no reason to believe, or we didn't pose the model in such a sense that there'll be some covariates or correlationship between the data points. So let me give you a couple of examples where this sort of idea comes up naturally. This the dependency comes up naturally. Like what and why is it not good to? It's not good to ignore it and assume they're independent data sets. So let me just try to sort of phrase the problem. Um, so let's go back to this classical example of smoking and blood pressure. Let's say. So, for example, let's say so. Let's say so. So, so suppose I want to understand effect of smoking and let's say blood pressure. Let me make it straight so that I can sort of maybe it'll be clearer. Handwriting will be better this way. Okay, so now I'm going to this. But what do I do first to understand this? I go to I go to a bunch of individuals, either they are smokers or non-smokers, and then blood pressure is a little tricky. So it can't be measured in sort of in one shot and you can get correct reading. So what you do is you make repeated measurements of the same individual, maybe at hourly intervals, and you do it for five times. Okay, so what you do is, so to do is we take repeated measurements perhaps for each participant in hourly intervals. So five. So we take, let's say, let me move this down. We take five repeated measurements at hourly intervals. So, intervals for each participant. So what does this mean? That means why are we doing this? We are going to do this to deal with measurement error and the fact that blood pressure fluctuates over time. Okay, so the reason for doing this is it's a medical reason. A practical comment told you is that measurement error we want to minimize. You want to account for that, and fluctuations in blood pressure. So that's how we take five measurements of the same person, right? So this is fine. So that means each person has five measurements, and so then there's an immediate problem, right? Because now what happens is that you have your five smokers, your each smoker or each, so your smoker and non-smoker. Let's say you have a. Let me draw a picture. Let me see if I can draw a picture properly. Let's see if I can get that done. Okay, let me try to get this done on the laptop itself. Okay. Instead of doing it like so you have sorry about that. Yeah. So you have, let's say smoker is here. I don't want to any fancy picture from my laptop. Smoker is here. You pick, let's say, five people, right? So each person we make five measurements, right? So let's say smoker one, let's say smoker A, B, C, D are the five or the four, or let's say four smokers I pick, and each person I do five measurements, right? So I do one measurement here, 1 hour, 2 hours, 3 hours, 4 hours, and fifth hour. The same thing I do, I go here and I go to the other side and I have non-smokers, right? So non-smoker, let's say I noted by yellow, so or blue, let's say blue will not come properly in this, yellow will come. So let's say non-smokers, and they're also aligned as A, B, C, and D, and I make five measurements, which is 1, 2, 3, 4, and 5. Right? So I do this for everybody. So everybody has this. So each of these guys is we make five measurements. Which let me copy this. So here's the thing. So, but what is the disadvantage of this now? You suddenly have some dependencies, right? Because these are repeated measurements. These are repeated measurements, right? Right. And all of a sudden, you're no more in the independent regime. So since these guys come from the same participant A, they're all not independent. They're all dependent. So suddenly you've introduced a random effect coming from a participant ID. Okay, so let's do this. So these are all. So the way we are like I like to think about it is that these observations come from same participant same participant, right? And so they are not statistically independent. They are not statistically independent. That's one. That's the first thing observe. And by this way of putting a participant through 5 measurements, we've introduced a random effect of participant ID. So that's one thing. We introduce a random effect of patient ID. And that's one thing we've introduced by this experiment. Even though your participants are selected randomly from a large population, that's okay. You're not really interested if one patient has a higher blood pressure than the other. That's not really a concern. You're only concerned about the class of smokers and non-smokers. That's what you want to understand. But you need to account for this repeated measure somehow, because each person is now correlated now. Like we'll have correlate measurements. And the other thing is that this person may naturally have lower blood pressure. So these 5 may be lower than this guy, and so on and so forth. So they're not IID observations. Okay. So, and the other thing is that these 5 dots have nothing to do with smoking, right? This class is, the whole class is smoking, that's clear. But each of these 5 dots being low or high is on the person, not on the fact that the person is a smoker or not, right? So if you don't deal with these random effects, what you're essentially doing is you're thinking of a data set as having independent replicates, right? And that's a problem called, in statistics, it's called pseudo replication. So that's what you're avoiding. So by introducing random effects model, you're avoiding what's called a pseudo replication. So if you introduce a random effects model like we have in class, what this helps to do is it helps to avoid what's called pseudo replication. Let me cut this off. Pseudo replication. That's what you want. So this is one. It's a problem here. Okay. So now what you might come and say, okay, fine. Hey, I don't want to do all this. Why do I bother? I have a good measurement system unit. I just forget about all these things. I just say I'll go and take only one measurement per person. So it means I go here, I just take this thing, and I come here and I say, okay, this is what I want to do. So an alternate procedure could be the following. An alternate procedure could be to sort of say, okay, fine, I don't want to do random effects. I want to go back to my fixed effects. Like think of it like fertilizer in the same homogeneous plot all the time. So I go and say, when I don't do this, I go and take only one fixed measurement. So here, let me put this. Let me remove this red bar here. I'll do this. Okay. But at the same time, now now you can say, okay, fine. Hey, I'll remove this fact that I have only one measurement per person. So now it's an independent observation. But then here also you can do the following. You can say that, okay, fine. What I will do is I'll just say,
I can't hear.
can you hear me now or no?
Yeah,
Hello?
now I'm able to hear you.
When did I stop? Sorry.
When you start off with that alternate procedure, I mean, a little bit just before you wrote those B's, D's are measured by N1.
Okay, okay, very good. So now I'll you can hear me clearly, right? Is it okay? Yeah, sorry.
Yeah. I mean,
Sorry. So the alternate procedure is I say, okay, fine. I don't want to do this mess of 5 measurements per person. I go into only 1 measurement per person. But then what I do is, this could very naturally happen in the experiment. The B's and D's are measured by nurse 1, and the 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 A's and the C's are measured by nurse 2. Okay, so these two people, these two nurses measure the blood pressure for these patients. Then, okay, I got rid of this replication effect by taking only 1 observation per person, but the nurse may have a slight variation. Every nurse may take the measurement slightly. So then here we have introduced a random effect coming from the nurses. So the nurse who did the measurement introduced a random effect. So if one nurse deals with all, so the other way to do is if one nurse deals with all, maybe the more natural one would be I'll write this way, maybe make it all this green. This may be the more natural way. One on smokers, and one nurse does with all non-smokers. So now, so let's say yeah. So this is like, let's this. So this is a natural way of a population being segregated and measured, and this introduces another random effect of doing this. Right? So this is something one has to be careful about. That is, any difference between groups that arises based on some other effect, one must account for, and that's why one always has to do this. You have to go beyond this fixed effects model where we assumed everything was independent to this sort of random effects model to account for these sort of phenomena. So is the motivation clear of why we do random effects?
yes, sure. Yes.
Okay, very good. So let me just make a new one. Make a blank notebook. Yeah. So I hope that sort of seals this is the one thing that you must keep in mind always. And this is a good example to keep in mind. There are many other examples that one can motivate random effects from, but this is a classic example to keep in mind. There's nurse and measurements, and smoker, non-smoker, and multiple measurements with a single measurement. And this is why you need a random effects model. I mean, this is exactly why you need it. And there are other easy examples to do also, but this is one thing to keep in mind. It's very tractable in the head. Okay, so now let's just go and just review the analysis a little bit, so that way I'll just set it up properly, so that you can sort of put it again, and then we just so maybe I'll pull up my notes on the website. Give me a second. Maybe okay. Maybe I'll leave the iPad. I'll rewrite the whole thing. Sorry about that. Well, the website link is not working. Is it for some reason? Okay, let me just check. That's why it's not loading up. I think I'll fix it today. Just give me 1 second. I'll just stop sharing and find the video. Sorry. Let me just go through the notes. So in the can you all see the screen? I'm sorry. Yes, no.
Yes.
Yeah. So this is the example I used in the class. I used a different example. I said your sodium content in a beer bottle. The data set that's there. There are 6 brands. Each brand has 8 and 12 ounce bottles were sampled and sodium content will be measured. Right. So now the same thing happens, right? So now here the random effects is the same idea, right? So you have expected value of sodium content for a given brand, it's like a given nurse, for example, or the sodium content differ between brands, and what is the expected value of sodium content in beer? That's one thing. And then what is the variability of sodium content between different beer brands? That's something that's the questions I posed, right? So now the way you can go back to the blood pressure model or to this model, the way one models it is that you you place a fixed effect that you already have in mind, and then this is the one we have now did before. We had mu plus alpha I and epsilon ij, where epsilon ij were independent, normal, zero scan. Now you notice that these are all fixed numbers. All the yij's were IID, right? The same distribution, right? Or not same, the independent observations coming from different means, perhaps. Right? So the independence was sort of very, very crucial in this analysis of this model, right? When we did this model, we had this chi-square test, and elementary statistical tests only played out when your underlying data set had independence. The moment independence is lost, you can't do those statistical tests that we did, this like the F distribution and so on. It's very, very hard to do. You just can't do that. So that's one simple observation. So let's just take this across. Let's just move across. So let's just say this is the. So let me copy this. Let me go back here to the live session. Let me go back here, paste, and then make it all white. So here let me do the old, let me come down here. In this case, they're all independent. So it's kind of funky that you have to keep in mind. This is all independent observation from the population. So there's no independence is crucial that we in all the analysis that we did. That is, our sum of squares are behaving like chi-squares and so on and so forth. Essentially came from independence. Right? So now we come to the random effects. Right? So here, the way I introduce random effect is that it's not a fixed effect anymore. It's not, it's like, so the idea is that this particular person will now play a random role. That means there'll be so at each level I'll have alpha I, which is random from a normal, and then there'll be some correlation. So even though epsilon and alpha are independent, across I and j there'll be correlations giving the alpha I coming, because the yij's are not have the same alpha I random variable running across all the i's. So this is naturally introduces a dependence particle model, and that makes the analysis a little bit harder. And that's what happened in this case. So there are many methods to do this, which we didn't cover in this class. One was this using this maximum likelihood, and we estimate fixed parameters and variance parameters and things like that. And I didn't go into the details, but the idea is that you need the number of observations to be large to do a sufficiently good analysis for this thing, if you do this for methods. And I explained this fixed effects and random effects system here between the two things, like I explained before. And what I wanted to test was that whether this variance was 0 or not. That means so all I did in class for you was that, is it true that the model is actually random effect? That is, if sigma squared is 0 or alpha or 0 or not. So if it's 0, then you have to do random effects model testing. If not, you go back and do a fixed effect testing if sigma squared is 0. So then here I showed you that the same test is true. That is, if you do a sum of squares alpha by RSS by n minus 1, that's like F, and the unbiased estimator is sample mean, and the variance is exactly the same thing like I had before. And then I also told you that this is how you get the constant intervals for the mean. And the correct estimator for this sort of sigma squared is exactly this SS alpha minus. So I didn't go and do the how to understand and analyze the random effects model. That'll be a whole class by itself. So I didn't want to go into that. I just stopped with just explaining to you. One must be careful. One must not sort of go and immediately do a. If there's an example like we did in class, like here, one must be careful to see that that you can't assume a fixed effect because the nurse is bringing a random effect, and here the many measurements are making these observations dependent in some correlated way. Okay, does that sum up broadly, or any clarifications you guys have?
Yes, Shiva, do you mind just pulling up the notes for week 11, the one
Week 11.
before this? Yeah.
Week 11, let me see. What is week 11? Week 11 is March 23rd, right? Let me just check. Just put it up. Okay, week 11 is only R codes what I have on the website, I think. Week 11 is there, no. April 1, it says. Let's see, April 1 is there. Okay, let me stop sharing here. I'll pull it up and then show it on the website, perhaps. Yeah, I have week 11. Yeah, go ahead. Yeah.
Can you
This one?
share the screen? Yeah.
I'm not sharing. I'm so sorry. I'm so sorry. This reminds me of this professor in Singapore once apparently held his whole class for 2 hours and just forgot to turn on the audio. Anyway, let's go. Okay, we're here now. Go ahead. Yeah. What do you want to ask me?
Yeah. So if you scroll down a bit, I mean, it will be good if I can just kind of at least have some pointed questions on this because I was just going through this.
Very good.
Yeah. If you scroll down further. So just one second. Yeah, just right there. If you scroll up a little bit, I mean, first of all, I don't know if it's important for me to be able to derive this because I'm not able to derive this expected mean square directly. I was able to do variance of y bar that I was able to get, but I'm not able to somehow derive this. I mean, of course.
This is just sum of everybody, right?
No, I mean in the ANOVA table, we have the expected mean square, the last column, right?
This one, I see.
Yeah, that is sigma square is kind of understandable, but the one above that for the treatment.
The treatment, how do you get n times sigma squared mu?
Yeah.
So that you just do a simple trick. Just add a yij and subtract a yij, okay?
Okay.
And this cross terms will vanish and then you'll get the exact answer.
Okay. So I'll try that.
It's a simple trick you can try.
Okay, sure. So that's one thing I had there. If you scroll down further, so this is fine, I think. So this, sorry, just that page. So unlike the sigma square that, so the sigma square estimate we have for the fixed effects model, right? That is for the error term, the error term, right? And that is just simply RSS by the degrees of freedom or whatever. So that's how we arrive at it. Whereas here, this is like the difference of.
Exactly, right. The treatment minus the error, right.
Treatment minus the error.
So you could potentially get a sigma square as negative. Okay, you could potentially get that.
Right.
That's something you have to be careful about. That's right.
Okay. So if you scroll down further, I think you go to the two-way and next. Yeah, if you scroll down further.
Yeah. My handwriting is not that bad. Huh? It's not. Sorry, I was very bad. It's legible. I'm surprised. Okay. Sorry. Sorry. Go ahead.
Yeah. So this table, just if you can.
Go ahead. Yeah.
Here, the interaction one, is that right? So should that be yij minus yi minus yj plus y bar? I mean, I'm just wondering.
Let me just
minus or plus.
This is the two-way random ANOVA table. I think you may be right. Let me just check my notes on my computer. One second. Give me a second. I think you may be right. Let me just check. Let me check my notes on my computer. I think I may have made a typo. You're right. So,
sure.
Also, like once you do this, I suppose I should type it up and leave it for you guys. I haven't done that. I should do it at some point. My notes. Let's see. I think I got it correct. Let's see. Yeah, you're right. It's the last one is a plus. I'll fix it. Huh? You're right. Thank you very much. You're right. This is a
Okay, no, yeah, this one.
sorry. Very
So
important.
this is because we are kind of the interaction bit is basically the mean of the interacting elements, right? So y
Correct.
bar
Absolutely.
of ij
Absolutely.
minus
Very good.
that.
Very good.
Okay.
Exactly. That's exactly that. Yeah. Right.
This
So,
expected mean square, I'm still
this
struggling
dot
to
is
get.
what I'm worried about, and I should just add the total overall mean. You're right. Sorry. You're right.
Right.
Yeah.
And the last one
Yeah.
should the error term should be yij or just y bar? Because that y bar is just the total sum of errors, right? Yij minus y bar.
Oh yeah, you're right. Absolutely right. Sorry, you're absolutely right. This is, I made a blunder. Let me
That
just
should be
go
just
back.
yij.
Yeah, yeah. Let me go back to my iPad and fix all these things once and for all. Sorry, I'm very sorry. You're absolutely right. Thank you for fixing this. Yeah, I'm sorry.
Oh.
Let me see if I can find this now. It's like April 1st, right? Let's see if I can find this. Sorry about that. Very sorry. I'll put it on the website immediately, but I'll check it. Where is the April 1 notes? Let me see.
At least in exams, I think we'll probably be given a cheat sheet.
Yeah, I'll give you a cheat sheet.
But
I'll check. Yeah, I'll have to go and check the cheat sheet is correct or not, but I think you're right. Yeah, sorry. Let me see if I can find it. I can't find it all of a sudden. Where are the notes? Let me see. Let me just put this two-way. Okay, I can't find it. I'll fix this. Okay, this you're right. This is YIJ. This is like you're right. This is a YIJ dot. You're right. I'll fix this and I'll fix it.
right. And one other question I had was in normal fixed effects model, your mean square error was simply sum of squares divided by degree of freedom, right?
Correct. Right.
The mean square, right?
Right.
Whereas in random effects, we go through this expected. I'm not able to get the concept, the idea behind it, as to why we go through an expectation of mean square.
Because see, it's not a fixed effect, right? So I'm trying to estimate the variance, right? So that's the expectation, right? It's not like uh, in the old case, the idea was that everything was deterministic in some sense, right? Like the effect was deterministic. I'm estimating the mean, right?
Right.
Here I'm estimating the variance, right? In some sense, right?
Oh.
So the variance is the mean, like you said here in the previous case when you computed this thing, is like it is the mean of this guy, right? That's the exact thing, right? So
Right.
that's what I'm doing the mean of, right? Because these are random points. I'm assuming them to be not fixed points, right?
Right.
That's what I'm doing the mean. Does that clarify?
Yeah. Just that I'm still not able to derive those, but I guess at least from given I have my exam.
I think that's algebra. Maybe I should put up notes for this how to derive these things. But I won't test. I wasn't going to test people on this, so I didn't do that. But I should probably do that. Yeah, I won't test you on these things how to derive these things. That's not.
Okay. So in a nutshell, for random effects model, we are really the hypothesis is that whether the variance between these different groups are the same or not, right? The variance is the same.
Zero or not? Yeah, zero or not, right? Like so, if sigma square alpha is zero or not, so we're checking, right? So here I didn't do I haven't done the overall doing how to deal with the random effects model. That's a whole different analysis. What I did in the class was just to ask you to test whether you have a random effect or not. So all I'm testing is whether sigma squared is zero or not.
Okay.
That's all I'm testing, nothing else.
Okay, that's clear.
Is the random effect there or not? That's all I'm testing.
Right.
I haven't told you how to go and analyze the random effects model. I'm not done that. That's another whole algebra complication. I didn't have time to do this. I stopped.
And do we also check whether the overall mean is zero or not? And is that where we use a t-test?
That's right. That utility is later on. Yeah. Once you confirm the fact that there's no fixed random effect, then you go and do the t-test after that.
Right.
So you know that y bar minus mu divided by this root is t, right? That's for the fixed effects model. You know that. There's one way test, right?
Okay. Yeah, I think certainly better than when I came to the problem. Thank you.
I hope it helped. This I see. For the issue, I think, is the following: that this would require another 4 classes to do this entire random effects model properly. But I didn't feel like neglecting it from the class because there's an important thing to keep in mind.
Right.
You can always do one way ANOVA and move on in life, but you have to be careful when you have random effects. So I just wanted to throw out that you should be careful. So that's probably where the mismatch happened. I think. I'm sorry about that.
Sure, and maybe just another silly question. So, in fact, in real life, when we come to applying these things, so we have all of this new machine learning and new stuff that we do, right? How do we apply this? Like, is it for us to test whether there's a correlation between these independent variables and different variable at an initial stage? First, do a level of testing and then kind of put them through a machine learning model.
I think the okay, let's say, so I'm not the correct person to answer this question precisely, but this is my first intuition. Now, in machine learning and other things, you need lots of data sets, right? You need lots of data points, right?
Right.
You just can't run with if you're doing a simple experiment with, let's say, 20 people. I mean, there's really no machine learning coming in there. You just have to deal data set. Right? You have to understand if the effect is random or not. Right? That's where these techniques come into play in a significant way. If you have large data sets and you're trying to brute force learn it, then that's a different model altogether. It's a different ballgame altogether. Just like you're doing optimization at a realization by realization level in some sense, right? So, in some sense, you have if this I think I'm maybe I should not be quoted on this, but anyway, I may record it, so I'm not sure. But essentially, you have the entire distribution there, so there's no error in some sense, right? That's what I would think of ML as in some sense. Here, I have a sample, so that's where I'm working with, right? I hope this course was a little different from other sort of machine learning sort of algorithm that you saw.
Yeah, it has been. So, I mean, one difficulty, or not difficulty, rather, one endeavor has been for me to try and figure out how this can be applied on a real data sets and so on. So
I mean,
anyway,
you
that's
can
something
always
I need
apply
to
it.
understand the theory
You can
before
always
it.
apply it, but unfortunately, if you have a lot of data, then I mean, you'll be able to get exactly the mean and exact variance very quickly. There's nothing to be done, right? So,
Right.
there's really nothing to be sort of in some sense.
May I ask something?
Yeah.
Like you have said, like the mu sigma mu square mean can be negative, like
The
sigma
estimate,
square.
the estimate, the
Yeah,
estimate,
estimate, sorry, estimate.
the
Then
estimate can be
what does
negative.
mean by negative? matlab, What
No,
it signifies?
that's just the estimate I have from the data set. I can get a negative value. That's why you should be careful about that. That can also happen. So you should discard it if that happens. Right? So,
Okay.
okay, if there are no further questions, shall we stop for the day and then sort of?
Yeah, I'm okay.
Yeah. Thank you for coming, and I enjoyed the live sessions a lot. I hope you all learned as much as I sort of enjoyed doing it. I'm sorry. I hope I didn't waste too much of your time in some sense.
I did. Thank you so much for
Yeah.
the time.
Yeah. Thank you. Okay. Bye-bye. I'll leave the meeting now. Thanks. Bye.